Now, I know what a lot of you might be thinking. Who would be, oh, let me be able to move my slides. Okay, who would want to program in C in this day and age? Isn't C that weird language that your seniors tell you not to use, that weird subset of C++ that's super unsafe? Why would we be interested in C nowadays? What value is there to it? Well, what if I told you that a lot of your ideas about C are actually false? What if I told you that there is more to C than meets the eye? What if I told you that if you challenge your preconceptions about this language and you explored it a bit more, you could uncover quite a lot of valuable ideas? I've been on a journey over the past 2 years. I've been coding extensively in C, not for work, for my own personal enlightenment. And in this journey, I've uncovered some incredible things, which I would love to share with you today. And in this talk, what I want to do is I want to present a modern way in which C can be used and address a lot of the misconceptions that people still have about how you're supposed to use C and what is actually C code. And I want to explore how these ideas inspired from C can improve our C++ code, and also how these ideas manifest in a lot of other languages nowadays. And I hope that all of this will be very interesting to you. And my name is Sas Luca. I am a core systems engineer at Creative Assembly. If you've heard of us, we're a game studio. And I'm mostly entering game development, low-level systems, and programming languages, as you'll probably learn from this talk. Now, let's start with a refresh on C, because you're probably, depending on your experience, not up to date with everything that's been going on. C is kind of an old language. It's been developed in 1972, so it's almost 50 years old. Now, 50 years is a long time. If you started, for example, with this book, the C Programming Language by Brian Kernighan and Dennis Ritchie, the famous C book, well, you might have quite a lot of misconceptions. For example, is this what you think of when you think of a function in C? Because this, what I'm showing right now, is the original syntax for functions in C. You can see that there's no return type. It's sort of implicitly int. Also, the variables in the function declaration were just mentioning the names and the types come after, which is a bit weird. Also, you had to declare all your variables at the beginning of the function, and you couldn't even declare your int I inside of the for loop. It was very weird. I think you also needed to put a parentheses around the return type. I'm not even sure about that. But yeah, luckily, C was standardized first by ANSI and then by ISO. It's kind of like C++. So maybe you've heard of a lot of C versions like ANSI C, C89, C99, C11. Now, C does still have an active ISO committee, much like C++. It's called WG14. And there are people who are, to this day, writing papers for C, and they are trying to add features to this language. So C is not a dead language. And, it's widely used, not just in legacy systems. There's the Linux kernel, which obviously many of you are probably using, but also a lot of embedded software and, of course, the dreaded legacy code that we're all dealing with. Now, what have we missed in the past 50 years, and how is C different from C++? This is what I want to start off with. And we're going to start with something very simple, comments. Now, in the original C, you only had the multi-line comments with a slash and star. The slash comments that were most commonly used to today, those were only added later. Also, variables and structs used to be quite weird. So as I mentioned, you had to declare all your variables at the beginning of the functions. And in C, for structs, enums, and unions, you actually had to decorate the type name with the keyword struct, enum, or union, which is quite verbose. There are people who still do this to this day. For example, in the Linux kernel, I think they do this, and it's just like a stylistic choice. But nowadays, you can actually type def the struct, so then you don't have to put struct or enum or union every single time you want to refer to it. You can also declare your variables anywhere in the function, so that is way nicer. There's also the primitive types that you're probably familiar with: unsigned, char, int, short, long, float, double. And these were the sort of the first attempt at portability with C, being able to use these types sort of for their purpose, and then they compile to different size types depending on your platform. But lately, they've actually added in C99, I think, this header called std_integer.h, and this header actually defines types of specific sizes. So now you no longer have to guess how many long or short or whatnot specifiers you need to use to get a specific size. And more interestingly, there are also these lesser known types called the minimum width int types and the fastest minimum width int types. Now, you're probably not going to use this unless you work on embedded or more esoteric platforms. But on those platforms, their design with these ones is that they give the compiler a bit more information. For example, with the minimum, the fastest minimum width int types, what they do is that the compiler can optimize a bit more if you're using it for counters, for example, or for indices in an array. It can, for example, decide that we can use some form of register in order to make this a bit faster. Now, functions, we covered this a couple of slides ago as well. As you know, the old syntax is was quite strange, as you had to put the types after you write the name of the function. Nowadays, nobody writes this code, as far as I am aware, because all modern compilers support the syntax that were mostly used from C++. Now, another important difference, however, is the following. Look at these two functions. We have a function called foo that takes no arguments and another one that takes void. Now, in C++, these are equivalent. They both just don't take parameters. In C, however, the first version means a function that can take an arbitrary number of parameters. So it actually is relevant in C to use void when you have no parameters in your function declaration. And this sort of brings us to an important point, which is that C++ is not C. And you might already be aware of this. There are quite a lot of incompatibilities between C++ and C. The main idea is that they're mostly compatible, specifically for headers, because then I can easily include a C header in my C++ code, and I can just use a C library. And that's very nice. Now, C++ did also inherit a lot of baggage from this attempted portability with C, which if you're at the C++ conference, you'll probably be hearing a lot of people complain about that. But what else is different between C and C++? Now, I'm not going to go over all the boring details. You might be aware of a couple of them. I would want instead to talk about what I think is one of the biggest difference, a killer feature in C that completely changed the way that I see this language and the way that other people see this language, and that C++ doesn't seem to have. And that one is struct initialization. I might be saying, well, C++ does have struct initialization, and in the C++, unlike in C++, C just has the structs in C are just plain old bags of data. It's what we would call pods in C++, but we can have those in C++. But C99 introduced this very new and powerful form of structure initialization, which is not present in C++. If we take a simple example here, I have a vector2 type, which is a pair of floats, an x and a y, and I initialize it on the declaration like this, and I just set the both variables to be 1, and this is fine. I can do this in C++ as well. Well, let's see what we can do in C++. Here, I actually specifically named the members of the struct that I'm initializing. This you cannot do in C++. There are some extensions. In GCC, your code might compile like this, but that's because you don't have the flags in order to tell GCC to disable its extensions. And this is very powerful, as you will come to see. Also, for once, you can actually initialize the members in any order that you want. I could initialize Y first and then X. Also, if you don't initialize a member, but you use this initializer, everything else is implicitly set to 0, which is, again, a very powerful thing, as we'll come to see. If you want, however, to set the variable after you already declared it with the struct initializer, you won't be able to do it like this, as you would expect, sadly. Instead, what you have to do is you have to decorate it with a type name in parentheses, and then it all works. Now, this is a bit of an incompatibility with C++, unfortunately. Usually in C, you would declare constants using macros. You'd have some macro that's some constant which expands to your initializer. But if you put the type name parentheses in order to satisfy C, that will not satisfy C++. Luckily, though, there is a simple macro that you can do in order to work around this limitation. In C++, you have this literal macro that expands to the type name in parentheses for C or to just the type name in C++. But yeah, let's go to a more advanced example. Let's consider another struct which has a struct member. What we're doing here is that we are initializing a member of the struct that is a member of bar. And here and everything else, if foo has other members, for example, or if bar had other members, and this is everything that we did, it would all be initialized to 0 by default. We can also have nested initializers. So here we're initializing f using the same initializer syntax as in B. If f was an array, we could also specifically initialize individual members of that array. So for example, at index 0 or index 1, we could initialize just index 0 and the specific member. We could initialize f of index 1 with an initializer. And also, this is a fun one, we can initialize the whole array and specify which element we want to initialize by putting the index in square brackets. And this can lead to very, very interesting API designs because we can easily initialize very complex data structure with nested initializers this way. And everything we don't explicitly initialize gets set to 0, which proves to be incredibly useful. And this is one of the features that I think leads to modern C. It is an awesome feature. In C++ 20, they also added a form of it, but it's not complete. So in C99, you're still getting a better experience, even though C++ is 20 years late to the party. So here I have an example. It might look intimidating, but don't worry about that. This is an example of a pipeline that describes, this is a graphics pipeline like you would have in a graphics API. And this is from a real library that's called so-called GFX. And what's happening here is that historically in C++, historically in graphics API, you would have OpenGL, and OpenGL is like a big state machine. And you have to remember to initialize all its state, then do your render pass, and then you reset the state, reinitialize it again, and all that. And if you ever make a mistake in all that state machine, then it's very annoying to debug. But here, what the Struct Initializers allows us to do is that we can describe our pipeline using this struct, and we can declare it anywhere we want. And then in our program at some point, we just say, hey, I want to execute this pipeline. And this is a very powerful declarative form of API that is quite unexpected in C. If you come from certain backgrounds, you might not expect that you can do something like this in C. You would expect it to be more in a higher level language. And also the way this pipeline works is that you're not initializing all of its members. You're initializing certain members, and those that are initialized to 0 can essentially be checked by the library and be like, okay, so for this, you want some form of default. And that is where the initialization to 0 becomes very powerful. And this is what I believe modern C is about. It's about challenging the ways in which APIs have historically been structured in C. So using newer features of C in order to improve the ease of use and safety of these APIs is what modern C is all about. And also in modern C, we are decoupling data manipulations from hosted services. So for example, instead of using a global malloc and a global fopen, we would be asking the user explicitly for allocators and IO callbacks. We would also, another characteristic is the centralization of resource management. So this might lead to, for example, allocator-aware design, which there have been some talks at this conference as well, and also system-wide resource management, which are now actually increasingly becoming popular in certain domains. So let's explore some other features and some more examples of C. Now, C11, which is one of the latest standards of C from 2011. There are newer ones, though C11 was a pretty big one. It added quite a lot of features. It's the latest or major version in terms of features. And as of recent, it's also supported by all the major compilers. It used to be that MSVC did not offer support for C11, but now it does. And let's look at some of the nice features that it added. It added static assert, much like in C++. Now, you have to include a header if you want to actually get the static assert function name. Otherwise, the built-in keyword in the language is underscore static assert, which looks a bit weird, but that's how they normally do it in C. Another addition is underscore generic, which is a facility that allows for overloading in C. So here I have a min f and a min I, which are min functions for floats and for integers. And then if you want to do overloading on them, you have to sort of explicitly say that you want overloading by defining a macro, which takes the arguments and then expands into this underscore generic call. And what underscore generics allows us to do is it acts like a switch statement on the type of one of the arguments. So in this case, I take A, and if it's a float, then I call min F. And if it's an integer, then I call min I. And this is a way by which you can achieve function overloading in C. Other additions that are very nice are atomics directly in the C language, though in older version, you can use libraries like C89 atomics, which essentially wrap the compiler-specific way of doing atomics. And also thread local, which if you're using, say, C99 instead of C11, is also available in all major compilers via extensions. And that is a common pattern that sometimes people do. When there is an extension that all major compilers support, you can usually, as a library vendor, it's quite safe to just wrap it up in a macro so that you have that feature. Now, talking about macros, let's talk about some awesome ways in which you can use macros in C. Now, a caveat, macros can be evil. We probably all heard horror stories about macros that become unreadable and generate undebuggable code and all of that. So we do need to be careful and use them in moderation. But I do think there are some cases in which they can really make our life much nicer. One awesome case that I really like is when I have an API that follows this pattern of having a begin and an end. Now, the problem with this is that, especially if you have a very long function or you have nested begin-end pairs inside of your functions, it can get quite hard to keep track of all of this, and you can get kind of lost in all of it. So, but by writing a macro, and I know it looks a bit intimidating, but don't worry. You can see in the lower left corner, what we're doing is that we are declaring on the same line, hey, in this scope, I want to run begin at the beginning and end at the end of the scope. And what this macro does essentially is that it uses a for loop. And inside of that for loop, it uses the comma operator to call the start and the end functions that you specified. And it also declares a variable which we are essentially appending the line number to it so that we can obfuscate its name. And then it essentially just runs a for loop just once. And in that for loop, at the beginning, you have the start function that you specify being called. And at the end, you have the end function that you specify being called. And this can be very useful. For example, if you want to profile some code, you often have to say profile, the profiler needs to start counting the time here and then end here. So it can be very useful for this. Another example is in immediate mode GUIs. This is a style of doing GUIs in which you do have begin and end pairs. Or another example of how such a macro could be used is to actually specify that we want something to happen at the end of a scope. So in this case, what I'm doing here is that I'm opening a file and then I'm specifying that, hey, at the end of this scope, I want to actually close this file. And this is actually a feature that exists in multiple other languages. In the Go language, for example, they use this quite often in order to close file. You would say, you would open your file and then you would write immediately after, defer, close the file. Also, some other languages that maybe you have not heard of, the Zig Programming Language and the Odin Programming Language. These are some very new, so they came out in the past 5 years, low-level systems programming languages, which have quite a lot of interesting ideas and are also heavily inspired from C. All of these languages, in fact, Go, Zig, and Odin, if you listen to their creators, they will talk to you about how they were heavily inspired by modern C code. Now, let's talk about API design in modern C. And I want to start with something simple, math. We all love math as programmers, I'm sure of it. Now, what I'm showing you right now is not how you would do things in a modern C API. This is sort of an old school method. So here we have our vector2 again, and we have a function that is supposed to add 2 of them. And what this function is doing is that it's taking a bunch of pointers. 2 of them are cons because they're to the data that we're going to read, the 2 vectors that we're going to add, and then an out pointer so that we can actually write the result. Now, this has a bunch of problems. Out params are harder to spot at the call side. They're not as nice. It's quite ugly to use out parameters. And also, there can be the indirection and aliasing issues because we're using a bunch of pointers. And that can actually harm performance. So how would we do this in modern C? Well, in modern C, we can just pass the vectors by value, and then we can just return the result by value. And this sort of value-oriented design is a very important thing in modern C. It turns out compilers nowadays are very, very good at optimizing passing structs by value and returning them by value, especially since in C, because of all of our structs are plain old bags of data, we don't have to worry about copy constructors, for example. So this design with this trivial object allows us to have a much nicer API. And also here, for example, I can use literals when I call my vec2 function, and it's overall just much nicer. I can initialize my result vector on the declaration. So, and performance can actually be better with this approach. And there are modern math libraries in C, like this is an example from Handmade Math, which is an open source modern C math library. And they follow this whole approach with all of their types, up to even like matrices with multiple elements. They just pass them by value and return them by value. And here is another interesting thing that you will notice is that this vector2 here in this library is defined as a union with a bunch of nameless structs inside of it. And what's happening here is that this allows you to refer to the same variables that say those same 2 floats in multiple ways with different names, but underlying it, it's just the same 2 floats. So you can refer to them as X and Y, or as U and V, or as left and right, or as width and height. And this can be very useful because now you can use this type in multiple places in your code base, but the names can actually visually fit what you're actually doing with the type, depending on the context. Now, for the next one, let's talk about error handling. When we think about error handling in C, you're probably thinking of something like this. You have a function that takes some arguments and an out parameter and returns an error code. Now, how you're supposed to use this is that you declare some error code variable, and then every time you do a task, you get the error from the return slot, and then you check for it, and then you do this again and again. And now some people thought, well, this is quite repetitive. I don't want to repeat myself. So they decided to use goto. And they just have a label at the end of the function. And, this approach can sometimes work. But if you know anything about goto, you might know that it's kind of problematic. There are some issues that can appear with it, some security issues, maybe in some very popular software that is used by millions of people around the world. So what could we do here to do better? What can we do in modern C? Well, I have here an example where I have a function that reads some file and returns the contents of the file. And the struct that it returns has a pointer to the data that we read from the file, the size, which is the length of the data that we read from the file in bytes, and then this valid member, which for all intents and purposes, it's like a Boolean. And what we're doing here is that once we read the file, all we do is that we check if it's valid. And when it comes to the actual error, say the file was not found, or the file was whatever happened, the cosmic ray hit your hard drive and something really bad happened. Those are usually handled in a centralized manner. So you would have something like a logging system for errors that would report these errors up. But in our context at the call site, all we know is, was I successful or was I not successful? Is the data that I got back valid or not? And this is the case because often this is what actually happens in real code. We don't have enough information at every single call site in order to handle an entire enum of errors. And not just this, but this pattern with valid here can compose very nicely. So let's look at a more complex example. Here I am loading a file. Then I am loading an image from that file, so sort of decompressing that image into an array of bytes. And then I am loading that as a texture. I'm uploading that as a texture on the GPU. And at the end, I only check if texture is valid. And the way this works is that if there was a failure at any point in this code, so say the file contents were not loaded or the image was not decompressed correctly, then that certain struct will be invalid. And then when I pass it to the next function, it will check whether the data that it's working with is valid or not. And if it's not, then it will simply return it. And this is quite similar to stud optional from C++. And there are actually proposals for C++ that were trying to achieve a very similar thing. So in this proposal from Simon Gran about monadic interfaces for stud optional, the idea is that you can get an image and then you can do a bunch of operations as long as whatever the return type is still valid. It's still there. The optional is true. And at the end, you just return it. And if at any point it fails, then the optional will just be false. And this is essentially what we're doing here in modern C as well. The big difference would be that we are packing this into the design of our data structure instead of having it be generic like stud optional. But at the same time, we don't have to do that meta chaining. We can just call our functions as normal, and it works very nice in the debugger, which is very nice. And as you'll notice here, we're working just with values. We're not working with a lot of pointers, which is really a good sign in modern C. And at the very end, we just, whenever we need to see the final result and do something with it, we can just check if it's valid. Now, it is also valid if you want to go with the route where you have an error code inside of your struct instead of the valid Boolean. That is a perfectly good approach. And in fact, it has parallels in other languages and in C++. In C++, for example, maybe you have heard of this proposal called stud expected, which is quite old. It was first introduced by Andrei Alexandrescu all the way back in 2012. And the idea here is that it's kind of like stud optional, but instead of a Boolean flag, true or false is the variable there or not, we have an error code. So we can actually handle more specific errors that have occurred. And new programming languages such as Rust actually have this as the built-in error handling module. In Rust, for example, you do not have exceptions. Instead, you have the equivalent of stud expected, which is called result in Rust. And you can see in this code, what happens here is that we are opening a file, and then we are essentially using pattern matching to check, hey, did I have an error? Where in that case, propagate the error. And otherwise, then great, I have a file. Let me do stuff with it, like read from it. And another language called Zig takes this even a bit further. In Zig, this mechanism is actually built into the language instead of being a library feature. So you'll notice in the first function, there's the exclamation mark right next to void. And what that represents is that, hey, this function can return an error. And then on our, we are parsing unsigned 64 integer, and then we're catching an error and handling it directly in the language. And on this other function, what we're doing, this other variant of our do a thing function, what we're doing is that we're using the try keyword, which in Zig basically means catch the error, and if there was an error, then return the error, propagate it. And this is a very interesting mechanism. What this essentially achieves is something very similar to exceptions, except the flow of how the exceptions propagate is explicit, And the second important factor is that there are no heap allocations. Exceptions in C++ do heap allocations, but here the exceptions are the errors are simply returned as values. And what's interesting is at ACCU in 2019, Herb Sutter gave a very interesting talk where he essentially presented a similar kind of mechanism, very, very similar to Zig's, but for C++. And I think this sort of shows that there is a lot of thought put in this, there's a lot of developments in the space of systems programming languages. And C++ is now evolving alongside many other languages. It is not the sole systems programming language where the whole discussion happens. Now, let's talk about generic APIs in C, because as we noticed with error handling, one of the problems was we have to sort of bake our error handling in the design of our data structures. Whereas in other more modern languages, we have templates. So we don't have to do this. We can just make a type like result or expected or optional, and that can handle all of it for us. Now, C does lack generic programming. I'm sadly not going to shock you here. I'm not going to unveil the latest C23 template proposal here. But because it doesn't have templates, it can it can kind of push us to think more outside the box and not rely excessively on templates. I'm pretty sure a lot of you know about the kind of abuse of templates that sometimes can happen in C++. So then let's think a bit creatively. What can we do with what C gives us? And there actually do exist some solutions for some very common use cases. So first, let's consider dynamic arrays. Now, in C++, this is probably the first exposure that many of you have to templates, which is making a stud vector, which is a dynamic array that we can push elements into, and we can have it be any type. It can be int, it can be string, it can be whatever we want. Now, here's how we can do this in C. We can just have our dynamic array be a pointer to that data. Well, now, okay, but a pointer is not enough, surely. We also need the size, the capacity. That's after all what the struct is, what the templated struct is doing in C++. Well, we can have all that info, the size, the capacity, and the size of the elements, since we're probably going to lose that type information. And what we can do here is that we can actually allocate a block of memory for our array, and we can place this information right before that as a sort of magic header that exists to the left of the pointer. So what we would be doing here essentially is when you're initializing it, let's say you're initializing a dynamic array with 10 elements initially. We would allocate a block of memory that is 10 times the size of the integer plus the size of that header. And then the pointer that we're returning is actually the pointer we allocated plus the size of the header. So we're going past the size of the header and directly to the elements of the array. And this is a bit hacky, I will admit, especially if you're coming from C++. It is definitely not as nice, but it does actually get the job done. We can then have a macro that we can use in order to add elements to our array. All we need to do is ensure the capacity, and then we get the size of the array and we dereference it, increment the size, and apply whatever value you passed in there as a macro. And this is quite cool. We now have dynamic arrays in C. And there are actually libraries that do this. One very popular one is by Sean Barrett. It's called STBDS. And his STB collection of libraries is very awesome, and I suggest that you look it up. And not just that, but with maps, you can actually do a very similar kind of design. In order to create a map, you just define a struct that has two members named key and value, which are your key and value. And then you can, using a similar pattern, we can implement hash maps in C99. And if you check his library, it has an implementation of a dynamic array and of a hash map using this method, and it's quite awesome. And now we're talking about libraries in C. I think it is worth mentioning that they were historically quite messy due to the multitude of build system and lack of a standardized way. In C++, it's a bit of a bad situation as well. And the library I mentioned beforehand called STBDS, it's actually what's called a single header library, which is sort of a very convenient and simple idea that people came up with in order to solve the problem with build systems, which is your whole library is in a single header, and the code, the implementation code is in that same header, but it is guarded by an if def. So in order to actually include the implementation in one file, you're supposed to include the file, and before you include it, define some sort of macro to tell it, hey, I also want the implementation in this one translation unit. And that is how a lot of libraries in C in the past years have actually been shared, just because it has been way more convenient for developers. Though I will say here, CMake is actually quite a nice choice if you restrict yourself to a sane subset of it. And single header libraries can actually be generated from like a regular library that has multiple files. So you can have the best of both worlds. And if you're interested in learning more about CMake, I would recommend this talk by Matthew Roppert from CPPCon 2017 about modern CMake. And if you actually learn how to use it properly, it doesn't have to be the nightmare that a lot of us probably dealt with in the past with it. And in newer languages, the library situation has improved drastically. Rust, for example, is well known for its very nice build system. All the libraries are centralized in a database that's handled by the developers of the language. It's all very, very nice. You just, in one line, you can get a library. Also, Zig takes quite a unique approach to having a build system, because in Zig, the build system is actually part of the language. So in Zig, in order to build your code, you would actually have an API in the language, and you write your build code in Zig, and then the compiler executes it at compile time, kind of like const expert functions in C++. But in this case, they can do literally build your code. Now, when writing libraries in C, I would like to give some advice. I would avoid allocations if possible, or request allocators or buffers from the users. I think this is very important, especially when people are very concerned about performance when it comes to C. Also, consider to try and make your libraries free-hosted. What free-hosted means is that you're not calling any functions from the operating system. So think like malloc or fopen. And if you ever need those, then you can just request them from the user. So here, for example, I have a very simple example of a struct which encapsulates a callback to an allocator that the user can fill out this struct and provide it to you. And all it does is that it has a pointer to some user-defined data. And this is important because certain allocators might not be global, so they need access to some extra information. And then there is a function pointer to this allocator function. And this might remind you of how in C++ 17, we got polymorphic allocators in C++, which essentially allow us to, which is a similar thing like this concept, essentially have this virtual polymorphic interface where you can define an allocator and actually specify dynamically at runtime for a specific object. Now, when it comes to memory management in C, that is where a lot of people have quite a lot of problems. But the reality is it doesn't have to be as complicated as you think. Now, what I would say is that in C, you have to change your approach a little bit. If you're going to malloc elements and free them at different places, it's going to be a bit messy. So consider instead to centralize your allocation. And what this means is that you sort of differentiate between your temporary and your long-lived allocations, depending on your system. And then you handle those in different ways, which might mean, for example, you have different allocators for them. And those allocators are actually responsible for handling the lifetimes of those objects. Another way that you can do this is by using buffers with maximum sizes where possible. Now, depending on what you're doing, this might not be possible, but you would be surprised. There are quite a lot of cases where this is actually a valid thing that you can do. And also, recently, there's been a lot of development in certain area, in certain domains, where we have systems such as entity component systems in video games. And the way they work is that you only ever work with handles. You never actually we don't touch pointers to the data. You have handles, and the system is centralizing all the allocation and is free to arrange them in whatever ways it sees fit in order to optimize them. And then you, at specific points, can request, hey, I need access to this data, give it to me from wherever you have it so that I can do my work with them. And when it comes to allocators, here is a very nice example of what you can do with them and how they can really simplify your code. And this is an example that is sometimes common in game development, to have what's called a temporary allocator. And what this temporary allocator does is that it has some large buffer of memory, sometimes called an arena. And as your game is running, during the frame of your game, you can make whatever random allocations you want. And then at the end of the frame, it will essentially garbage collect everything that accumulated during the frame. So it's basically a very basic but very fast garbage collector. And it's often implemented like a stack. So when you make an allocation, all it does is move a pointer, and that's it, and you have your memory. And this can be very useful because it leads to better performance because your allocations are much faster. And also, you're essentially have all the lifetimes managed for you. It's the lifetime is the scope of the frame that you're working in. Now, as we've seen already, API design in modern C is more declarative and functional and less stateful. It is more value-oriented. There are less pointers. It is quite different from what we're usually used when we're thinking of C. Zero initialization is used very heavily. There is even a term for it called ZII, kind of like RAII. It stands for zero is initialization. And what we do is that we use a lot of these new features from C99 and C11 in order to modernize our code. And we centralize our resources and we write our code in an allocator way fashion, and suddenly it feels like we're in a completely different language. It's very different from the kind of messy C code where you're trying to emulate other languages when it doesn't really fit. Now, let's talk about one of the biggest problems that people have had historically with C, which is string handling. String handling, for some reason, people really struggled with string handling APIs in C. And historically, it has been just a complete and utter disaster. I mean, we all know the horror stories about how null terminated strings have caused unmitigated security problems and whatnot. And this is in part because of the terrible standard APIs, which probably made sense in their day and age, like the 70s. Functions like stir or stir talk or stir-p-burk. But yeah, public service announcement, just avoid the standard C library. The standard C library has quite a lot of traps. It's very old, very slow in some regards, and it just has kind of terrible API design. There are obviously some useful parts, the std.h that we mentioned before, memmove, memcopy, memset, math.h, which often just wraps the math instructions of your processor. These are quite useful to have, but a lot of the other stuff like the string functions, those quite a disaster. And if you actually start thinking about replacing parts of libc for your purposes, you can end up with APIs that are so much nicer. For example, here I have some code where I have this custom struct and a function that can pretty print it. And what I'm doing is that I have my own custom logger, and thus I can register that, hey, when I have the cat string inside of my string, my format string, then I want you to call this function called print cat. And then I can just print my cat. And it's so much nicer. It almost looks like the new stud format API from C++, C++20. And this is just because I've realized, libc, it's useful sometimes if you want to write something very quick, malloc, fopen, printf, they're useful because they're there. But if you want to write something serious, I heavily recommend that you consider replacing those because you can have so much nicer APIs. It feels like a completely different language once you actually do it. And oh yeah, as we mentioned, null terminated string, they're like the devil. And they're quite literally awful. Like even recently, a couple of weeks ago, I'm not sure if you heard of this, but a modder actually managed to reduce the loading times of GTA Online by roughly 70%. And the problem was they found in the code that GTA had is that they were parsing JSON files, and they weren't parsing that much data. It's like 10 megabytes. You know, game developers, they did with gigabytes of data. So what's this all about? Well, sadly, the developer who wrote that code decided that it was a good idea to use the string functions from libc. So they used scanf and specifically strlen, which caused a lot of issues because with strlen, in order to just get the size of the string, you have to traverse it, which essentially trashes your cache, which is a very important aspect in modern programming. And simply by removing all of this and adding some very basic code that caches the string length values and whatnot, it ended up in a 50% performance improvement. And this was done by a modder, not by some official Rockstar employee. So not to trash Rockstar developers, it is understandable that developers sort of gravitate towards the standard library, but in C, we sort of have to make this realization that libc is just not that good. And we should look for replacements of this. And those can enable us to write much, much better code. And sadly, it's not just null terminated strings. There are a lot of bad patterns related to string handling, sadly, in systems languages. As a case study, let's take stud string from C++. Now, consider this function. I want to read a string, and so I take a stud string const reference. And my intent here is, hey, I have this string that I just want to read it, okay? I don't want to do anything with it. I don't want to type it. I just want to read it, okay? And what do you think happens if I call it like this? So I have a string literal. This exists in the data segment of my executable or my library. What happens when I call this function? It allocates. Well, why does it allocate? Well, it allocates because stud string isn't really just a string. It's more of a string builder. It has to keep a pointer to its data on the heap. Now, I will have a caveat here with this very tiny string, because we have some clever optimizations nowadays, like small string optimization. This wouldn't actually do an allocation, but if I had a couple more letters there, it would actually cause an allocation. And you might say, well, what's the problem with a couple temporary string allocations here? There surely is not a big deal. Well, I would disagree because I use this browser and it's called Chrome. And in Chrome, half of all the allocations are stud string. Well, you might say, I mean, these are Google engineers. They're very, very good at what they're doing. And Chrome is an incredible piece of software. So, you know, they're probably justified, a lot of them. Well, for example, in the past, they had this discovery that apparently when you type one character in the omnibox, that is the top bar in Chrome, the search bar, that results in over 25,000 allocations. Now, I am not an expert in how Chrome works, but given by their response at the time as well, I don't think that was intentional. I don't think those 25,000 allocations were intended. And you can see right here, bam, 25,000 allocations just there, you know, magnificent. Computers are quite fast, you know, it's quite impressive. But yeah, the reason why this was happening was because they had a lot of implicit conversions between const char star and stud string. So they would have a function with a char star that they then use to call a function with a stud string, which they then use to call a function with the char star, and it converts implicitly. And then they call another function that takes a stud string, and so on and so on. And this massive chain resulted in thousands of allocations here. And now in C, we don't have implicit conversions and constructors. So that is a bit of a good step in the right direction, at least when it comes to string handling, because when I worked in C, this actually motivated me to make a stronger distinction between owning and non-owning strings. So when I developed my modern C string API, I declared these two structs. One is called stir, which is a simple pointer and size pair. And the other one is called stirbuff. And this is actually like a proper string builder. It has an allocator and a capacity, and you can append. Oh, sorry about that. You can append to it and you can do other operations. So if we look at like the operations that you can do on a stirbuff, you can append to it. You can create one with an initial size and an allocator. You can append strings to it. You can insert strings into it. You can remove strings into it. You can convert it to a stir if you just want like a view of the buffer. And you will notice here that this API is quite nice. I'm not sure how a lot of you are feeling if you haven't worked a lot with modern C code, but when I initially coded in C, I would see pointers everywhere and error codes returned and out parameters. And this is just so much nicer. It feels almost like a true modern language. And when we look at the stir functions, we can see this even more clearly. There are no pointers. There are no pointers. Where are the pointers? There are no pointers. Every single function takes values and returns values. And this value-oriented design makes it so much easier to work with C. And I want to talk about one function, which was so cool when I made it. And it's called stir pop first split. And what this function does is that it takes a pointer to the source, and then it takes another string, like a delimiter that it can split by, and it returns to you the first result of that splitting operation. And here I have an example. So I'm making here from a string literal, I'm making a string, that's the date, and then I'm essentially popping by splitting with the forward slash. So I first get the year, then I get the month, and then I get the day. And what's nice about it is that all of these are just string views. There are no allocations happening here anywhere. All I'm doing is that I am modifying my original date string, and then with these other ones, I'm just getting a new pointer and size pair. Now, consider how you would do this in old C. If you were to just Google how to do this in C, you might probably stumble over a Stack Overflow post describing something that looks kind of like this. So this, we also have a date, and we have our year, our month, and day, and we're using the stirdoc function. And you might look at this and say, well, it's not that bad, but it is actually once you start looking into the gory details of this. So first off, notice how this stirdoc function returns a char star. But at the same time, we can print it with printf. With printf expects a null terminated string. Where's the null terminator? And what I realized when I was writing this code, because I never used stirtalk, so I had to look it up online, is there's actually a bug in this code. That date should actually be an array on the stack. Because what stirtalk actually does behind the scenes is that it keeps the pointer to your original string. So as you can see, I initially passed date, but then I passed null. And after that, what it does is that it inserts null terminators into this string that I'm giving it. And that is just a legendary level of unintuitiveness and just sort of insanity, I would say. Not just that, but if you were to do this, for example, with a string that you have from somewhere else, well, you would have to make a copy of it. So already you have to start doing useless allocation just because they are really, really trying to push a null terminator design. And again, in historical context, this probably made sense. It was probably kind of sensible at the time, it was fun and all. But nowadays, this is just horrendous. This is just evil. You wouldn't even dream of such an API. But if we look at the modern C version, it's quite nice. I wouldn't have a problem writing this daily at work. It's very sensible. And we can even make it better. We can, for example, add overloading such that we don't have to wrap our string literals with that cstir function in order to convert it to a stir object, because we can just check if the parameter is a const char star. And in that case, our overload does that conversion. So there we go. Now the API is even nicer. And this is readable. It does no allocation. It is much safer than the insanity that was stirred up with the global state and all of that. Yuck. This is so much nicer. This is what modern C is all about. And if I am to show you yet another crazy awesome macro, this macro, again, looks a bit intimidating, but what it does is that it essentially wraps that behavior where we called pop first split into a for loop. And if you look at the usage code that's down, you can see that what I'm doing is I'm specifying the name that I want for my iterator, so to speak, and I give it the string and the delimiter. And behind the scenes, it generates this for loop that essentially goes through all the string. And here I am now lazily going through all of these, to all of the splits of the string, instead of having to, for example, split it and store all the results up front in an array, which is an extra allocation that I do not want to do. Allocations can be expensive, especially if you're not using like super custom allocators everywhere so that you can hyper optimize your temporary memory allocations. It is much nicer to evaluate things lazily and not have to deal with allocations at all. And this is actually interesting because the first ever optimizations when I did when I joined Creative Assembly was kind of related to this. What was happening is that there was this seemingly cheap function that was splitting some strings. And it turned out that that function took quite a lot of time, but it wasn't very obvious. If you were to just look at it, you would think it's just a blip on the radar. But luckily, our profiler that we use called telemetry is quite good and has this interesting feature called an accumulation zone. And an accumulation zone basically tells us what's the cumulative cost of this code over time. So there I could see, oh, wow, it's taking quite a lot of time. And when I looked into it, what I did is that I replaced it. I replaced the solution, which what the code was initially doing was splitting a string into multiple strings inside of an array. And I replaced that with a solution that was non-allocating, would just lazily evaluate, lazily split the string into string views from C++17. And that way I removed all the allocation there. And it was quite a significant improvement. It was like a couple of seconds from what I remember. And these are sort of good examples about the pitfalls that can happen with the way that we're dealing with strings. So, and other languages now, they have also been noticing this. In Rust, for example, this stir type that I've been using here, Rust just have it by default. It's built into the language. It's not even a library feature. In Zig and Odin, for example, they have built-in array view types, which are also have like string manipulation functions. Java and C# also follow a similar model. If you're using the string object in Java or C#, those are immutable. If you want to do a lot of operations where you're modifying the string or whatnot, you're supposed to actually be using the string builder. Luckily, in C++, we did get some improvements regarding this. Granted, 17 years late, but still better than ever. So we got std string view, which you should absolutely consider using as a replacement for const std string ref. And also in C++ 20, we got std span, which can work as a array view for an arbitrary type. And this can replace, for example, using const std vector of whatever ref everywhere. So that can avoid more allocations. And also ranges. Ranges is this new API in C++ 20, which allows us to build these very complex, lazily evaluated, non-allocating algorithms. And they can, again, be very useful in solving these problems that we can encounter. So in conclusion, what I would hope is that you gain a better appreciation for what you can do, even in a limited language like C. I would encourage you to check out the latest development in C++, but also in other systems languages, in Zig, in Odin, in Rust. And I would also encourage you to re-examine some of the patterns and preconceptions that you may hold, because once we actually start challenging those, then we can actually start improving. If we just take things from granted, if we're just going to use libc because it's there, we're going to end up having incredible load times like GTA 5. And we don't really want that. We want to have very short load times. So by challenging our current understanding and not taking things for granted, we can discover new and better ways of doing things. And I would also like at the end to give some shout outs, because this talk was inspired by an article by Andre Weisflog called Modern C for C++ Pips, which also covers a lot of the things that I've covered in this talk. I also encourage you to look into the Odin, Zig, and Rust programming languages. I think we're going to hear a lot more about them in the following decade. And also some other languages that I would throw out there, D and NIM, those are also very interesting. And I would also give, if you're interested in learning more about C and finding other people who are working with C and love it, I would encourage you to look at Handmade Hero, which is a great online series that where they code an entire game from scratch in C. And also the Handmade Network, which is a community of people that are really interested in low-level systems programming languages and how to improve things, how to challenge our preconceptions, and how to make things better. Yeah, thank you. And if you have any questions, I will answer them now. Let's see. I got here a comment that there are aggregate initialization in C++20. I would say, though, I should have made a slide about this. There are some caveats. As far as I'm aware, there are certain things which you cannot do in C++ that you can do in C99 with their initializers. So there are a couple of differences. One thing from C that you would like to see in C++ and the reverse. If I wanted a thing from C++ in C, it would definitely have to be templates, just because, they literally make life easier. We are able right now, to do dynamic arrays and hash maps, but it would be nice as long as it's not abused. Also, interestingly, from C++, what I discovered is methods. So where you have the object, that method notation. One of the unknown advantages of that is that you don't have to sort of namespace your names as much. In C, I often namespace my function names quite a lot, just because I don't want to have to deal with collisions. So I would have like stir underscore buff underscore make or underscore append or underscore whatever. But in a language like C++, you can just say my stir buff dot append. And it's a bit nicer, not as verbose. But yeah, one thing from C that I would like to see in C++, in terms of features, well, designated, the initializers were like a big one, and we sort of got that. So I'm quite happy to see it, though it is a bit incomplete. I need to look up all the details again. Sorry, I should have made a slide about the differences. There is a slight nuance there. And yeah, what else? When working in pure C, do you feel references and auto values are allowed, or should it be kept pure? So if you can clarify here a bit, when you mean about references and auto values in C, because in C we don't have references, we only have pointers and values, and auto doesn't exist in C. There is an auto keyword which meant a thing a long time ago, but nowadays isn't very useful. So if you could clarify a little bit there, I would appreciate. But in general, in C, I just pass a lot of things by values, and sometimes I have to pass things by pointer, and it's great. It works pretty awesome. And I've talked to a lot of people who've also been trying C, and it's quite interesting how it acts like a palette cleanser. This is what I would talk about C. If you want to try C in like your free time, it will act as a palette cleanser. If you're coming from the C++ world where we have all our crazy features and tons of new compiler improvements. And yes, I mean, when working with the C++ compiler, to compile C code, this is okay to borrow those C++ features in a C environment. So there are people who do that. There are people who use restricted set of C++. There are articles such as Orthodox C++, which talks about essentially a minimal subset of C++ that they deem to not be overly complex. In Handmade Hero, I did say they're using C. It's technically not true. They're using C++, but they're using very few features from C++. They are using, for example, overloading, because they weren't, C11 didn't have support in MSVC at the time when they started. So because they wanted overloading, they decided to use C++. And there are a couple other niceties. You don't have to type def your structs, for example. Oh, the restrict keyword. Thanks, Dimitrios, for reminding me. The restrict keyword is another very cool thing from C. Though if you work with a lot of values, you actually don't need to use it that much in C. Maybe on some very low-level functions, sometimes it can improve your performance. But in C++, it'd probably be very nice if they added it. But I imagine, I know there's quite a lot of debate about that in C++. But, even in C, you don't have to use it that much if you just pass things by values, especially in math code. Like in the past, you're probably using restrict there because you're passing everything as pointers was helpful. But nowadays, you just pass everything by value and it's fine. You don't have to care about that. Yep. Any other questions, or are we running out of time? Or I'm not exactly sure how I'm supposed to end, when I'm supposed to end everything here. But yeah, if no one else has any questions, I would like to thank you all for coming to my talk. I hope you enjoyed it, and I hope you have a great day. And I guess we can end here. Thanks.